Okay guys, this is the tutorial that follows up the course on chemical representations and file conversion, and also how to draw structures using some tools. Right, so we'll start somewhere. We're going to start from OpenBabel. As you can see here, OpenBabel is an open source tool that is used to draw, manipulate, and handle structures, even up to 2D, 3D generation, molecular fingerprints, similarity search, and everything. So it works on both Windows, Linux, Mac OS, and whatever. So if you're interested in the OpenBabel GUI, there are instructions on how to install them here. Right, so yeah, so basically that. So most of the commands, most of the instructions here are usually for developers. You want to build from source, you want to, a whole lot of codes. Now to just have OpenBabel that is within reach, you can actually install it yourself on your command line. So remember, this is our working directory, the demo directory where we work. And then usually you need to, if possible, you can create a conda environment to wrap around them as a container, or you can just install it at the base. So you can create a conda environment. So if you run this command conda install OpenBabel from conda 4 channel, so you can install OpenBabel. Now I already have it installed, so I'm not going to allow it to run. But usually it just install pretty fine, and then you can check, oh, how is my OpenBabel working, by just looking for OpenBabel, and then it's going to say, oh, this is how to use it. To look for more options, OpenBabel -h, and then it's going to give you all the possible things that it wants to use. So this is just like an abridged summary. There's a lot of functionalities available on the website if you want to look at it again. Okay, let's just start very simple. At the graphical user interface, this is what OpenBabel GUI looks like. So you will always have an input file format from where you select, and then you have a way to load your file, and then you select a lot of options. Should I add hydrogens? Should I append input file name to title? So a lot of options, total mass, and everything. Then you specify the output formats, and then possibly the output directory where the file is supposed to go to. And you click convert, it runs. So this is usually how you run on OpenBabel. There was someone working on molecular modeling and you want throughput. You don't want to be on the GUI, you want to be on the command line. So I'm going to show you how. So I'll be using VS Code to just explain a few of the things about OpenBabel, right? Okay, so this is my VS Code. As you can see here, I've written the code. So the codes, the Jupyter file it will be made available. So these are my codes, and I can actually, from where I'm running, I can install OpenBabel from pip. I just showed you how to install it from conda. So you can also install OpenBabel from pip. So I'm coming to RDkit. I'll talk more about RDkit later. OpenBabel, you can install it from pip, from conda, just from different distributors. Yeah. Okay. So I'll try to run it first. So let's install OpenBabel and RDkit and see how it goes. So it's going to ask us for an environment. So these environments are some of my interpreters based on Python that I use for some of my work. So I always work on this data analysis. So that's my interpreter. And so I think in the Python tutorials, you have seen how to, create your own conda environment, install your libraries, and then, you can select it here as an interpreter. Okay. Now it's connecting to the kernel, then it will start my installations. It just take maybe a few seconds to be pretty fast. Okay, it says requirements already satisfied, so I already have OpenBabel as you can see, and then RDkit requirements. So everything I already have them. Obviously, I know I have them, but I just want to show you. So now let's explore. Now, why am I putting exclamation mark in front? So if you are running a bash command on Python, so you need an exclamation mark in front of it. Yeah, before it to be able to run. So that's how it recognizes a bash command, right? So because OpenBabel is built on bash, there are also there are Python wrappers, but basically it's on the command line. Okay, so let's look at the functionality. If we ask for OpenBabel minus H, so we're going to see the same thing we saw on the command line. You can see all the options that are possible, usage, how to run it, and everything. So let's look at just a few examples. So we're going to convert a molecule. So this is already my working directory, the demo that I showed you before. So we're going to convert molecule1.sdf to molecule1.mol, right? So we're going to make that conversion and then add hydrogens and something like that. So it's very simple. You need to call the input molecule, then the -O flag for output, then you call the output for a molecule with the exact file format as an extension. So SDF as input file format, mo as. So if you don't want it that way, you can also call an input file. For example, you can call an input format, for example, -I SDF as my input format. So it will recognize that. So anytime you call an input format before you call the file, the format here overrides any extension that is here, right? So you might as well have a file without extension. So if you call the input extension, it will recognize it. The same way for output, if you specify an output format, so the same way it will override this one. But usually, if you don't want to, you can just call your files directly and then run it. So it's a very simple command. One molecule has been converted, and then we can see molecule1.mol, which is here. So that's actually how to work with OpenBabel. Now, OpenBabel is very easy, very fast, and then since you can use it on the command line, you can loop over structures, make them very, very fine. Very, very fast. Now, usually, if you're working with library and databases, compounds are delivered to you as multi-entry. So you have a single file containing 200,000 molecules. It's called multi-entry. It can come in different file formats. It can come as PDB. It can come as SMICE, as SMI. It can come as PDB-QT. It can come as whatever, but they are multi-entry files. So in one single file, they append all the structures, separate them by some conventions. They have different, as you move from one file format to another. Yeah, but usually this is how it works. So here I'm showing you a file, which is a SMILE file that has around 2,000 molecules, just called library.smi. And I want to convert everything in PDB. So now how do I do it? It just requires me to call -m flag. If you can see from here, I'm not sure whether it's written here. Yeah, -m is somewhere here, so you can see more details later. Yeah, but -m is also here. Look at it for splitting. So what -m does is that if you have what I call compressed, but it's not actually compressed, it's just a multi-entry file. If you have that kind of file, -m will go in and extract all the ligands one by one and make the conversion for you. So just bear this in mind. For example, if you're working on drug repurposing and request for all the drug from drug data bank, request from the drug data bank. So what is going to happen is that they're going to send you a single file containing all is an SDF file, usually an SDF file containing all the drugs that are in their database. So you're talking about thousands of structures. So you need to use the -m command to extract all the molecule one by one. So what is going to happen now is that since I called an output.pdb, I'm going to realize that it's going to make the conversion, and then all of them will be out. All of them will carry the name outputs, but the numbers will begin to change. Output 1 for the first molecule, the output 2 till the total number. So I have, as you can see here already before, because I ran this code, if I have 2000 molecules. Yeah, 0 to 1999. So 2000. So let's run and see what it's going to give us. So it will start doing the conversion from the library SMI to PDB file with the -m flag, extracting each of the molecules one by one. So it's done with the conversion. I now have 1999 molecules converted. It may not show here, but if you just take a peep here, you might as well find out that our screen is filled. So don't worry, I'm going to delete it later, but you can see our screen is filled up. It has done the conversion outputs, append the number. So each of them is a valid molecule. So that's actually how you do. And the same way you can convert multiple molecules into a single file, compress them. So it also works both way. Okay. So now, okay, so it showed up here. Okay, now why do you need to use OpenBabel on the command line? It's just very simple, because you are considering throughput, the ability to plug your code or your command into a pipeline. You understand? Maybe your docking pipeline, your virtual screening pipeline, whatever. So imagine if we have now all the compounds that imagine if you have PDB compounds in library. There's a library folder here, which by the way, it's empty, but I'm going to go and populate it with some compounds now so that I'll be able to run this. But imagine we have PDB compounds there, all right? And then we want to convert all of them to mol file. You get in a loop. If we have so many PDB molecules, we can loop over them, as you can see here, and then use OpenBabel to convert them, let's say from PDB files into mol files. So, and that's what we are going to do now. But just a minute, let me make sure everything is fine here. Yeah. So I'll run this, and then it's just going to convert a few molecules. Some of them will bring up warning, especially for some molecule that it cannot calculate the structures, but that shouldn't be like a very big problem, right? Okay. So it's done. It's just a few molecules that, initially I reduced the number so that it won't take us a lot of time. Okay, so that's for OpenBabel. So OpenBabel has a lot of functionalities, and then for starters, you are invited to have a look at it. As you can see here, come to the guide and explore the full functionalities of OpenBabel. Now, to move on, we are going to talk about RDkit, because RDkit is now the next generation structure manipulator available for chemoinformatics, machine learning, AI, and everything. So this is the official page of RDkit, starting RDkit in Python. So as you can see, it has the whole functionality, the whole tutorials and examples on how to use it for a whole lot of things. So you can come here to follow the usage of RDkit. But let's just see some basic things about. So in RDkit, in fact, as of today, RDkit has replaced OpenBabel as the tool of choice in most chemoinformatic workflows, right? Okay, so let's just have a peek on what it looks like. So first of all, let's try and convert one of our molecules in SDF file into a PDB file, and then good. So this is one of our molecule from SDF into a PDB file. So don't worry, it's already in 3D. That's why the structure is looking this way. So if I came mol from file, so from RDkit import came, and then mol to PDB file, then output is PDB. So this is actually what it does. So you see, this is something that OpenBabel can do. but I think RDkit does it even so much better than OpenBabel. So I have a list of smiles here and their names. So let's try and display them. So we are going to convert them from smile list into mole images, right? So yeah, you can see that. So isopropanol, tetrachloride, and acetic acid. So that's actually how it works. I remember the last time we spoke about canonical smiles, I mean in the course, and we mentioned that if your data set it has a lot of compounds, you must canonize your smiles. And the reason is because if you don't do that, there'll be a lot of replicates. Yeah, because smiles can be written in 1001 ways for just one molecule. So how do you try to achieve that? Let's assume we have this list of smiles. All of them are valid smiles for pentane. So what do we do? So I think first of all, how do you like convert everything to the canonical smile? So I think for example, here we're going to demonstrate that if we first of all convert it to a mole object, here a mole list because there are 5, and then we convert them back into a smile notation, all of them are going to have the same smile. So it's just I think that is exactly how RDkit handles it. So if you have a lot of compounds, I mean, if you have a particular compound with a lot of smile notation, convert all of the smiles into a mole object, convert it back to smiles, and all of them will appear back in the same smile notation. So, and then you can easily use that to do filtering, because if there are duplicates, you cannot remove them, right? Okay. So I've converted all of them to RDkit mole object, and then I can now send them back, and eventually it just brings out a single simple smile for 5 of them. So I can now see, if I judge by this alone, it will appear that I have 5 molecules, but now I only have 1 molecule because all of them are actually pentane molecule. Okay. Now, I also thought something about smarts. So if you're working with libraries, how do you query your library? How do you search it? If you want to retrieve all the compound that has a benzene group, how do you go about it? So that's where smart pattern come into use, right? Okay, so this is a smart pattern that will allow us match a benzene ring attached to a single carbon. So as you can see, this is what it looks like. A benzene ring matched to a single carbon. Yeah, so this is exactly what it looks like. So if we are querying our database and we want, so this #6 means carbon, #8 means oxygen, and so on and so forth. So you can do a whole lot of things here. So you can see, so you can query and match your compounds by just these strings. So with that, you can do scaffold searching, you can retrieve a lot of compounds from your database and all that. So this is the end of the summary uh, for the demonstration on using OpenBabel and RD. And then don't forget, I just showed you how to use OpenBabel from the Python interface. You can still use OpenBabel from the command line. Yeah, you can use it from the command line very clearly, just that it is very easier to demonstrate here on the Jupyter Notebook. So special thanks to resources provided by Pat Waters and then directly from the RDkit page. So this is just a very brief introduction. A lot of things can be found in these links. Okay, so before we close, let's just have a very small idea about drawing chemical structures. I know this is a bit outdated, but it's still something you should have in mind. Yeah, so I'm going to demonstrate to you how to draw your chemical structures using one of the free tool out there, which is a Chem Sketch. We have a lot of these kind of tools, Chem Draw. A lot of them are even embedded in web services. Yeah, so you can find a lot of them, Avogadro and so on and so forth. Now, why this looks a bit outdated, I still find it very useful because so many times you are trying to build your system and you want to build it from scratch. You don't want any molecular software to make the conversion for you, especially when you're not working in a batch. If you have like 1,000 compounds to work on, you don't want to come and draw them. But if you have a particular ligand that you're trying to optimize, maybe using some quantum mechanics to calculate some partial charges. You want to construct it yourself from scratch, and you might have the need of these drawing tools. So I'm going to demonstrate how to draw this complex structure. So this is an alkaloid, a polyphenolic alkaloid, as you can see. So I'm going to demonstrate how to draw it on using the ChemSketch here. So the ChemSketch interface is this way. You can pick up molecules from here. You can pick up atoms. You can draw a bond. You can draw series branching bonds, continuous bond line. You have chirality specifiers here. You can do a lot of things. So we're just going to show how to do it. So how do I start drawing the structure? I think it's simple. I'll just start from this scaffold. So click on benzene ring and I drop it. And I look for the hexane ring and I also drop it, right? Okay, so then I'm going to continue my journey from here. I will do this, then I'll do this, right? Okay, I think I need to take a step back. Then I will add another benzene ring. Oh, the benzene ring, it's not okay. So I'm just going to add it here. Then I can connect the dots. Good. So this is a good way to draw it. So if you click on carbon and then you come to the bond here and then double click again, it becomes a double bond. It can become even a triple bond, and then on and on. You can come back to a single bond, right? Okay, now having done that, I can also add this, right? I can add this. Okay, then I'll also need a benzene ring somewhere here. Then I will complete the ring. Yeah. So I think that's already very fine. Okay, I'll also need a bond here. I'm coming over to this other substructure, and then I'll need a benzene ring here, then a phenyl ring here. Good. Then I will complete this. Good. Fine. Then I'll need a ring here. Then I'll also complete this. Good. So we're already taking a shape. Then I'll add the comma. So usually how you work with this is you draw the scaffold without minding the heteroatoms. For example, as you can see, I've not added any heteroatom, the oxygens or the nitrogen. So when I'm done drawing the scaffold with carbon, I can now add some of those things, right? So that's actually how to do. So this is all methyl. So obviously it's going to have an extra methyl. Then for here too, I'm going to have a methyl group. So because there are two substituents, which is an explicit hydrogen to show the protonation. So it's better I do it this way. So if you click, it will add the bond automatically. But if you don't like the direction of the bond, you can actually draw it yourself. Just click and drag, click and drag. So, and then I think I also have a bond here. I also have an O methyl here. So basically this is the scaffold of my structure. So I'll now go back to heteroatom replacement. So I have my oxygen here. I'll add it here. Oh, sorry, I missed it. Add my oxygen here. Then add my oxygen here. Add my oxygen here. Okay. Also here. Also here. Also here. Then it's now the nitrogen. Here I need a nitrogen. Obviously, it's become charged because it's already quaternary, becomes charged. Then the hydrogen, I'll need to also replace it. So because it has an explicit hydrogen to show the protonation. Right. So this is basically my structure. Then I'll need the chiral center. So for example, the wedge bond, I'll need here. The hash bond, I would need it here, right? So this is my structure. So sometimes you are preparing a ligand. Usually this is not necessary. As I said, if you're working in throughput, you have a lot of compounds. But if you're working on a single compound and you don't want issues with any software, you want to build it yourself step by step and make sure everything is clear. You want to come and draw it. First of all, you can use ChemSketch, ChemDraw, Avogadro. A lot of the drawing tools are available to build your molecule from scratch, right? Okay, now that I'm done drawing, I can I still my cursor is still in draw mode, so I can click here. So then if I click at the center of the molecule, it select the molecule, I can move the molecule. Then if I want to rotate the molecule, I can click here and then can rotate the molecule. Then if you also want to rotate it in 3 dimension too, I can do the same thing. So you can see my molecule, right? So that is that. Then if I want to delete anything here, at the same time, I can come and look for my eraser and say, oh, delete this, or delete that, or delete whatever I want to delete. Okay. So, well, that is just by the way. Another thing that we can do is from this smiles, I can ask for, I can ask, oh, generate, sorry, from the structure, generate the smile notation for this. Do you get? So I can also ask, oh, show aromaticity, add explicit hydrogen. I want to see all the hydrogens or whatever. I can ask, oh, convert it to 3D structure, 3D optimization, and so on and so forth. So these are the things that I can do, and a whole lot of more. You can specify reaction, can draw your reaction structures and whatever, a whole lot of things here. Yeah. So what else can I show you? So when you are done, what do? You can actually save this. Yeah, and also, even in Chem Sketch, you can actually, uh, generate a structure from smiles. For example, you can actually generate structure. For example, if you ask structure from smile, to ask you to add a smile notation and to draw the structure for you. That might be a very simple way to at least start up what you are drawing, because if you have like a very large scaffold, you may not have the strength to draw everything from scratch. So you might want to first of all start from use this smile notation and generate the initial structure and start to optimize it the way you want and add some important maybe substituents that you want. Okay, so when you are done, you can actually decide, oh, I want to save out this, export or save as, whatever, and then you choose very important file formats. Sketch, it's just proprietary, it's not a transferable file format. So you might look for MOV files, SDF files, which are easy to transfer. These are usually the two most important file formats that you might want to use. Okay. So, and then that is it. So this is actually how to draw your structure, build your structure from scratch, add protonations where they're supposed to be, make sure your structure is nice. And as I mentioned again and again, it's not suitable for throughput. If you're working in throughput, you want to use OpenBabel or RDkit or whatever is available to you. Yeah. All right. Thank you. I think this will end the demo for this session. Yeah. Thank you for joining us this far.